So first off, the database that ICM uses and the unique engine that it has, that proprietary ICM engine I mentioned, the Workgroup database is what we call it. And essentially, what we see typically with a lot of traditional models is you might have a master copy sitting on a server. Somebody will copy that out and start to make some new scenarios and make some kind of changes and tweaks to that. Well, somebody else makes a copy of that one and does something else with it, like a permitting review or development. And what happens when you start to deviate against that? How do you merge all those changes together and put them together in a succinct way to have an archived file ultimately to get back to that master copy? Ultimately, it leads to a lot of confusion. I know I've spent probably days trying to dissect and understand what happened in a model, and it just really kind of gets people to hoard work and has it so it's less collaborative in general. The Workgroup database is much different than this, where you still have that central copy of a model sitting on a server. It can be on a local computer as well, but the idea here is being able to check out a copy of that model. And through this whole routine, multiple people can check out that master copy. And as at a point, you'll need to commit that data to the database. And what that does is allows for merge and conflict resolutions between the two. If there's two people editing the same data object, which one's going to be right? Also allows you to go back to previous points in time, again, having an undo redo button within each one of those commit sessions, and just overall making it a better environment for being able to understand where the data came from, work with other people, and be able to go back to previous versions if that's necessary. There's also a data flagging feature. This is also pretty unique to InfoWorks ICM, where you can create flags for any number of reasons, whether it's somebody's individual edits, if it's coming from GIS data. This can just be helpful to understand how a model got built and kind of what the values are and what you can say is safe to replace. So if you have some missing data in your GIS, you can go ahead and fill that in with inferred or assumed data and flag it. Once you get better data down the road, you know exactly where to go and make those changes. Additionally, you can make flags for individual team members. This can be helpful just to make sure you understand what gets changed by who, and so you know who to go ask and talk to about that. There's also inferencing tools in here. So looking at the selected pipe here, we've got the properties. We've also got some inline validation. You can see the gaps in the GIS data. These validations are going to be for both informational warning and errors. Errors are going to be things that need to be fixed, but the warnings and errors don't necessarily need to be. But things like the upstream invert, of course, you need those for being able to run a model and get a hydraulic simulation to go. So the idea here is selecting this entire profile and then using an inferencing tool to fill in those gaps of the data, either by, and there's a couple of different options for how exactly to do that. You can pick up ground elevations for manholes on based on ground models and be able to infer things like the upstream and downstream inverts based on the bottoms of each of the nodes, different things like that that are handy. As you'll see here on the right side too, all that data gets flagged, so it's not like a blind box and you're not understanding which values are going to be changed. So cloud capabilities works exactly the same as the Workgroup database, except that server is now on the cloud. This allows for the same kind of collaboration, but also allows for unlimited storage. As these models get bigger and bigger, especially with ground models and things like that, these can be relatively large. Didn't mean to go that. Relatively large, and so having that kind of unlimited storage. There's also the capability of running a simulation on the cloud, so being able to leverage all the hardware and things like that in the cloud. I did some testing on my own. This is an example of a bunch of different simulations running simultaneously. For a 1D system that really just takes a few seconds to run, I ran 1,000 different simulations on it. And in the cloud, took about 6.5 minutes. Not too much slower, just doing it on-prem. But again, the 1D systems are typically easier. I did this again with a 1D, 2D model and did 3,600 simulations. Took a little bit over 2 hours for all of that to run on the cloud, and tried it again on my local computer, left it running overnight, and it still wasn't done when I got back to work the next morning. So I just gave up after 17 hours, shut it down. Based on the progress, it probably would have been around 24 to 30 hours, but pretty significant savings in terms of time there. This is also a quote from one of our kind of early adopters or earlier adopters of the cloud running in the database. They were running about 6 simulations. Each one was taking 2 to 3 hours, and a total runtime of over 12 hours for everything. After they moved all their data to the cloud and started running them there, each simulation took about 2 minutes, and they could run them all simultaneously. So a huge impact on the efficiency of the project. So again, just looking at kind of model management of everything, I did mention a little bit earlier, there is the time series database that can be integrated into the model database too. Again, just a central hub for GIS data, other models being brought in, that version history, data flags. The time series data allows you to link directly to things like rain gauges, flow meters, radar rainfall, pump status, and really just about anything else, anything that has a value and a time associated with it, that can be integrated as a time series data to help with simulations or calibration purposes. The typical way this is done is you'd have a sensor network, you have a SCADA data database, and you request data out of that database, and usually there's some manual processing. You might also match it up with radar rainfall. A lot of this can be a very slow and time-consuming process, and with the time series database directly linking to those data sources, you're not able to have not having to do all of that manual work to get that data into the database. And this can be particularly helpful for running radar simulations. There are both scalar and spatial time series databases that can be integrated here. Spatial really is just that something has a location, time, and value, versus scalar is just a time and a value. So radar rainfall would fall under the spatial, whereas something like pump status or would fall under the scalar database. You can also match up to flow sensors. So this is an example looking at an overlay. And on the next slide here, showing an example of how you can integrate with the time series data and overlay the observed data with the model data in order to get a better understanding of how well things are calibrated. For this one in particular, it has a flow meter on it, and you can see down at the bottom there, the kind of brownish color being the model data and the goldish color being the observed data. You can zoom in, it's going to sum the volumes for you. You can create scatter graphs in this dialog as well to see if you have a nice one-to-one relationship between the two, and then export out to CSV for further types of statistical analyses.